Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the exergy, working potential of energy. The first law of thermodynamics deals with the quantity of energy and asserts that energy cannot be created or destroyed. This law merely serves as a necessary tool for the bookkeeping of energy during a process and offers no challenges to the engineer. The second law, however, deals with the quality of energy. More specifically, it is concerned with the degradation of energy during a process, the entropy generation, and the last opportunities to do work, and it offers plenty of room for improvement. The second law of thermodynamics has proved to be a very powerful tool in the optimization of complex thermodynamic systems. Preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. For an energy source, what we really need to know is the work potential of the source, that is, the amount of energy we can extract as useful work. The rest of the energy is eventually discarded as waste energy and is not worth of our consideration. Thus, it would be very desirable to have a property to enable us to determine the useful work potential of a given amount of energy at some specified state. This property is Exergy, which is also called the availability or available energy. In fact, not all energy sources have the same availability, that is, from the perspective of how much energy can be converted into work. The available energy in different forms of energy is different. Mechanical energy and electrical energy are fully available. All of them are available energy. Thermal energy does not have complete availability, even though an ideal reversible cycle, thermal energy cannot be fully converted into mechanical energy. For example, more of high temperature energy can be converted to work, and thus it has a higher quality than the same amount of energy at a lower temperature. The spontaneous heat transfer process and the eventual attainment of equilibrium with the surroundings are shown in the figure. An object at an elevated temperature Ti placed in contact with atmospheric air at temperature T0 eventually cools to temperature of its much larger surroundings. To conceptualize how work might be developed in this case, see the figure. The figure shows an overall system with three elements: the body, a power cycle, and the atmosphere. The atmosphere is presumed to be large enough that its temperature and pressure remains constant. Wc denotes the work of the overall system. Instead of the body cooling spontaneously as considered in the first figure, this figure shows that if the heat transfer during cooling is passed to the power cycle, work can be developed, while heat is discharged to the atmosphere. These are the only energy transfers. The work is fully available for lifting a weight or equivalently as shaft work or electrical work. Ultimately, the body cools to T0 and no more work would be developed. At equilibrium, the body and atmosphere each possesses energy, but there no longer is any potential for developing work from the two because no further interaction can occur between them. If the initial temperature of the body were less than that of the temperature, in such a case, the directions of the heat transfer would each reverse. Work would be developed and the body warms to equilibrium with the atmosphere. The useful work potential of a given amount of energy at some specified state is called exergy, which is also called the availability or available energy. A system is said to be in the dead state when it is in thermodynamic equilibrium with the environment it is in. At the dead state, there can be no interaction between system and environment, and thus no potential for developing work. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment, that is, the dead state. Exergy represents the upper limit on the amount of work a device can deliver without violating any thermodynamic laws. There will always be a difference, large or small, between exergy and the actual work delivered by a device. This difference represents the room engineers have for improvement. Note that the exergy of a system at a specified state depends on the conditions of the environment, as well as the properties of the system. Therefore, exergy is a property of the system-environment combination and not of the system alone. Altering the environment is another way of increasing exergy, but it is definitely not an easy alternative. Distinction should be made between the surroundings, the intermediate surroundings, and the environment. By definition, surroundings are everything outside the system boundaries. The intermediate surroundings refer to the portion of the surroundings that is affected by the process, and environment refers to the region beyond the intermediate surroundings whose properties are not affected by the process at any point. Therefore, any reversibilities during a process occur within the system and its intermediate surroundings, and the environment is free of any irreversibilities. The atmosphere around us contains a tremendous amount of energy. However, the atmosphere is in the dead state, and the energy it contains has no work potential. Okay, that's all for this task. Thank you very much, and see you next time.